All right, so here we have a system of objects question. It's a little bit trickier than most because we have three blocks rather than just two that are involved. So we have a bit more things to pay attention to. We're also given a paragraph description about what the motion is. Specifically that the blocks are going down the incline, not up. So that tells us something about the direction of the frictional force. We're also told the magnitude of the various frictional forces, that they're not the same on the two blocks. And we're given bits of other information about the masses, but not numbers, right? And we were working on an incline as well, so we have to be dealing with vector components sometimes. So, the first step, even though the problem is complicated, the first step really isn't. It's just a free body diagram for one of the blocks. Right, so we have one block, and block M1. So we know it's moving down the incline, so that means we have to have a frictional force, kinetic friction specifically, up the incline. It has a mass, so that means there's a weight force, or the force of gravity, and it's not going through the incline, so there's a normal force that is perpendicular to the incline. And finally, there's a string that's attached to it that points up the incline as well. So there's a second arrow here, T. Right, actually I'm going to make that. There's no reason those two forces have to be the same length. So I'm going to draw them to be two different lengths. Right? We don't know anything about them, just the direction. So kind of like that. Right, four forces. Okay? So, now we've done part of the setup, and hopefully that reminds us that we might need free body diagrams for block 2 and the hanging mass, capital M, as well, but we've done one of them. Alright, so the first question is asking us, what is the coefficient of friction between the inclined plane and block 1? Right? And so this one actually, if you don't think about it carefully, you can get yourself in a bit of trouble here. Because we're given information about the frictional force. We know the force of the friction is F. Right? Actually, I guess I should really go back up here. Right? And I shouldn't label that with a subscript because we're given that exact number. Right? We're given this thing as part of the problem. And we also know the definition of kinetic friction. So the friction force, by definition, is mu k times n. Right? So if we knew the normal force, we would be done. We don't need to do anything else because we know the frictional force's magnitude. So if we can do that, then we can solve it pretty easily. And we do know something about the normal force because we know that this thing's vertical acceleration is 0, right? It stays on the incline, right? My coordinate system looks like that. And if this is my y-axis, we know AY is 0. So that tells us that we have one force, we have to talk about the components of the weight force, right? And so this length right here is W sine theta, right? Oops, sorry, that's cosine, right? Let me erase that. It's the side that is adjacent to my angle theta, right? So W cosine theta. And we already know the normal force is entirely in the vertical direction. So if we write the net vertical force on block 1 is 0 because of that, then the normal force minus the weight times cosine theta, or m1g cosine theta, equals 0, or the normal force equals m1g cosine theta, which we can then substitute right up in there. And so, and if we rearrange to solve, we get mu k is F over m1g cosine theta, right? So it's possibly easier than you might have first thought. Okay? So, that's part B. Now we have a little bit more work to do for parts C and D. Part C is definitely the hardest part of the problem. I think it's the most time consuming. We're trying to figure out the value of the suspended mass m that allows the blocks to move with constant velocity down the plane. Right? There are a couple different ways that you can do this. And I'm kind of unsure what the easiest way to present it is. So if the way that I present here doesn't make sense to you, or you can't see what I'm kind of visually doing, then ask me about it directly, because I possibly show you another way. There are lots of ways to set this up. When you have complicated systems, there are always many ways to solve them. So what I'm going to do is I'm going to say that yes, our picture, right, looks like this. Right? But because these two masses move together, we don't really care that they're separate. So I can solve this problem, right? This is as if, because it's going to answer the problem, it's going to be numerically, it's going to be the same setup, as if it looks like this, where this is the combined mass of the two blocks, and the frictional force is the combined frictional force, right? F plus 2F, right? Because we're told that that's the total amount of friction, right? And this is now a problem that's a lot easier to solve. I could treat every single block separately and have a system of 3 equations and 3 unknowns, right? I'd have 2 different tensions plus the acceleration. That would, or rather, I would have 2 different accelerations plus the value of the hanging mass. One more time. 2 different tensions, right? I'd have the tension in this string, the tension in that string, and then the hanging mass would be my 3 unknowns. But like this, I only have 2 unknowns. There's the tension in this, and there's the hanging mass. And so this is going to be computationally easier to solve, and it's going to behave the exact same way if I make this substitution. So I'm going to do that on the next page. So my new combined block, so this has, oops, let me do that in a different color. So the free body diagram for my combined block, right, there's the weight force, there's the normal force. So we want it to move down the plane, so there's a tension, up, and there's 3F, up, right? And then my hanging mass, we have capital M, G, and T, right? So you can immediately see that here's our unknown, and there's our other unknown. And everything else we're going to know in the problem. Since constant velocity means the acceleration is 0, we'll be able to solve it. So, since I need something with this capital M, I'm going to say that the net vertical force on that block is 0, or T minus capital Mg equals 0. So if we knew the tension, we'd be done. We don't, but fortunately we have this. We have the other block. So, we have to write the net horizontal force, because that's where that tension appears, equals 0. So if we're going to say the acceleration is 0, then we're going to get that the tension plus 3F, right, because those are in the same direction, minus part of the weight, right? If I do my components of the weight again, it's the exact same, but now it's the other component. What I care about is this bit. That's mg sine theta, or in this case m1 plus m2 g sine theta equals 0, right? And so we can solve this for t. T equals m1 plus m2 g sine theta minus 3f. Then this just gets plugged right into there. And so we get m1 plus m2 g sine theta minus 3f minus capital Mg equals 0. And if we move the capital Mg term to the other side and divide by g, we get our result that capital M equals m1 plus m2 sine theta minus 3f over g. Right? And so that's our answer. Right? Because we're able to combine those two blocks that move identically into one, it was a pretty easy process. It's much more algebraically intensive if you can't do that. It is still solvable if you treat each block separately, do a free body diagram for each block, you just have more to keep track of. Okay? And so finally, part D is kind of a nice closer, right? Part C is tricky, but part D isn't quite so bad. So the string between block 1 and block 2 is cut. So we go back to our free body diagram, and now it's going to go down the incline, right? We know what the frictional force up it is. We have a weight, and we have a normal force. Well, we're trying to figure out an acceleration, so that's a horizontal force. Right, so we're going to write Newton's laws like that, and all we need to care about is what's the horizontal component of the weight, right? This piece, which we kind of have already dealt with. It's the sine term. So down the incline is going to be our positive direction, so m1g sine theta minus the force of friction F equals m1a. Right, and this is actually really simple to solve because we know everything except for a, so we just divide. So g sine theta minus f over m1 equals a. And we're done, right? Because the string was cut, we no longer have a system of objects, so it's once again pretty easy to solve. Right? Part C is definitely the time-consuming part. And so this is another point when I make a useful test-taking comment, right? If you can't do part C, that doesn't mean that you can't do part D, right? Part D took me about 30 seconds. Even if it takes you a little bit longer, you can still do that part even if part C is tricky. So make sure you look at all parts of the problem. Sometimes you can get free points or easier points in places you might not expect. It's not always getting harder from the start to the end.